climate scenarios have this overshoot idea in mind.
Overshoot is exactly what it sounds like. Average global temperatures rocket up beyond what our civilization can survive, but by then we're pulling greenhouse gases out of the atmosphere because we've saved our existing forests, restored others, and even built a bunch of carbon-sucking machines.
Oh, we're going to go ahead and blow past all these targets, but then we'll bring everything back down again, and trees will be sequestering the carbon back again. But the ability for the trees to do that really depends on how steep we go up that curve and come back down.
Jason Funk is an environmental scientist who runs the Land Use and Climate Knowledge Initiative, or LUCKI. He's one of my go-to experts on forests and climate change, and has been ever since we first met at the Poznan Climate Talks in 2008.
So if it's like really sharp, like the Matterhorn, and we go up and it's super pointy at the top and then we fall back down again, that's really bad for these dynamics.
Yeah, they're going to be wiped out.
Exactly. Yeah. And then we'll have a lot of dying forests that won't be able to shift in response to that really steep peak.
Right.
Back in May, he sent me a paper called Long-Term Thermal Sensitivity of Earth's Tropical Forests, which looks at whether forests can continue to pull carbon from the atmosphere as temperatures rise. What they found is, it's complicated.
If instead it's more like a smooth curve, like Kilimanjaro, then these trees may be able to persist and all these other dynamics can play their course and play their role in this drama and may be able to mitigate that effect. So they're still around. They're still around to play that role later. We have less turnover and a more durable terrestrial biosphere that's going to be able to help us out of this predicament.
Okay.
Man may be unwittingly changing the world's climate through the waste products of his civilization.
There's a group of us now who are proposing that the Earth has actually entered a new epoch, and that is the Anthropocene.
We know that the enemy is carbon, and we know its ugly face. We should put a big fat price on it, and of course, add to that, drop the subsidies.
Earth, we broke it, we own it. And nothing is as it was. Not the trees, not the seas, not the forests, farms, or fields. And not the global economy that depends on all of these. But we can restore it, make it better, greener, more resilient, more sustainable. But how? Technology? Geoengineering? Are we doomed to live on a bionic planet? Or is nature herself the answer? That's the question we address in every episode of Bionic Planet, a podcast of the Anthropocene, the new epoch defined by man's impact on Earth. And today we address it from the familiar perspective of tropical forests and how these forests can and can't mop up greenhouse gas as temperatures rise. I recorded the actual interview in late August on Jason's front porch. He lives down the street from a hospital, so you'll hear occasional ambulances, and we were beset by many plagues, cicadas, mosquitoes, and of course, we always have COVID-19. But I learned a lot, and I hope you do too. Also, I have to apologize for the long hiatus between episodes again. We took on some projects at Forest Trends that required a lot more of my time than anticipated. The good news is that these projects have given me an opportunity to dive really deeply into issues related to ecological restoration, and they'll make some great shows in the future. But I still need your help to produce them. We're in a weird spot right now in terms of climate coverage in the news. The issues that I care so deeply about and have been covering for decades, such as natural climate solutions, green supply chains, and deforestation, and of course the general interplay between economy and ecology, they're all showing up more and more in the mainstream media, which is great. Unfortunately, the same news outlets that so long failed to understand the enormity of the climate challenge are now failing to understand, let alone explain, the solutions available to us and their limitations. If you like what you hear on Bionic Planet, if you think I'm doing a good job of translating these issues into plain English and putting them into context for you, and you want to hear more, then help me give it to you by becoming a patron at patreon.com/Bionic Planet. That's Patreon, Patreon.com patreon.com/Bionic Planet. There you can support me for as little as $1 per episode and with a monthly cap. This way, if I don't manage to generate an episode in a month, like once it just passed, you don't get charged. And if I manage to crank out a ton of episodes, which is what I really want to do, you don't get whacked either. The address again is patreon.com/Bionic Planet. That's patreon.com/Bionic Planet. You can also help by helping others find the show by giving me a 5-star review on whichever podcatcher you access me through. Remember, the more stars I get, the more ears I get. And the more ears I get, the more minds I can reach. And we have to reach hundreds of millions of minds if we're to meet the climate challenge. We can do it if we all work together.
We're looking at this paper that came out. It's called The Long-Term Thermal Sensitivity of Earth's Tropical Forests. And now here come the cicadas again. They're firing up just as we get going. We've always had this idea that if we save the forests, we can help absorb all this extra carbon dioxide that's in the atmosphere. We can reduce climate change. And then there's also been this fear that as temperatures rise, trees are going to stop absorbing carbon. And that's also been out there.
Yes.
And then there's this third element that the more carbon is in the air, the more carbon they have to absorb. And what this is saying is you've got these two competing factors going against each other.
Yes.
That's the gist of it. Okay.
So
Yeah.
a lot of people forget that forests are like in flux all the time. They're growing, they're dying, they're storing carbon. Some of it is in the long term, over the lifetime of like trees that could be centuries old, or in soil where they're stored for a long time. Some of it is as ephemeral as the leaves that grow one year and drop off and decay away in a single year. So this paper is looking at those types of dynamics over time, and then how those things are going to change in the future in response to climate change.
And these researchers or organizations, they're all part of this network. It's what's it called?
They are part of the Rainfor network, and that's a network of tropical forest plots. They've been collecting data there for decades, and they keep resampling them as a way to keep monitoring how are these forests changing, what's going on here, what are the dynamics. And a couple of years ago, maybe 2017, this group published a couple papers looking at what was happening in the Amazon, what's happening in Asian forests, and finding...
And African forests.
And I think there was one for African forests as well, yes. There was this assumption that these forests would be in equilibrium. They wouldn't be sequestering any more carbon, that they would be in balance between the decay that was happening all the time. We call that respiration, where microbes and the trees themselves are breathing just like we do. It takes energy to metabolize to just keep them running. Mm-hmm. What's cool about plants is they have the ability also then to photosynthesize, to take in carbon dioxide from the atmosphere and give off oxygen through photosynthesis. Both of those processes are related to climatic factors like temperature. Mm-hmm. They speed up in response to temperature.
Let's do a quick refresher on high school biology. Photosynthesis is what this podcast is all about. It's how plants use the energy of the sun to inhale carbon dioxide and exhale oxygen. Some of that carbon mixes with other chemicals to become carbohydrates, which the plants use for energy. But another way, they convert light energy into chemical energy. Then comes respiration, which I haven't talked about that much on this show. It's the opposite of photosynthesis because it involves breathing in more oxygen to help break down the sugars from photosynthesis so the plants can grow, just like we do. Now, we'll soon hear from Jason how excessive respiration wears plants out. If they work too hard, they run out of gas. They get tired. People are like that too. And I'm a person. I want to produce more of these episodes. But if I've got to make my living tending to other projects, I don't have the energy. If you like what you hear and want to hear more, then you can help me deliver it by becoming a patron at patreon.com/Bionic Planet. That's patreon.com/Bionic Bionic Planet. There you can support me for as little as $1 per episode and with a monthly cap. You can also help by giving me a 5-star review on whichever podcatcher you access me through. Remember, the more stars I get, the more ears I get. And the more ears I get, the more minds I can reach. And we have to reach hundreds of millions of minds if we're to meet the climate challenge. We can do it if we all work together. Now back to Jason Funk and our discussion about photosynthesis and respiration.
Both of those processes are related to climatic factors like temperature. They speed up in response to temperature, and that's what this paper begins to look at. So we have this increase in carbon dioxide in the atmosphere that acts like fertilizer for these plants. At the same time, you have an increase in temperature that has a bigger effect on the respiration part and a lesser effect on photosynthesis. So that means the trees are burning more energy, they're metabolizing more, and that's using up that energy faster. So this paper, for the first time at this extent, looking all across the tropics, is trying to understand that temperature effect.
Okay. What confuses me right now is they're breathing faster, right?
Yes. Mm-hmm.
So they're taking in more carbon dioxide and breathing out more oxygen. Shouldn't they be holding more? Like, why does, if they're breathing faster, why does that mean that they're storing or absorbing less carbon?
Yeah. So here's an example where the breathing metaphor is not quite
Okay.
it breaks down. Through photosynthesis, they're taking in carbon dioxide, as I mentioned, and that process has a maximum. It depends on how much sunlight is hitting the plants, and that depends on where their leaves are and if the canopy, how it's oriented toward that sunlight coming in. So one aspect of that is the plants are getting their energy through this photosynthesis process, this engine, and the sunlight is the catalyst for that, or allows that to happen. That's where the energy comes from. They're grabbing these carbon dioxide molecules out of the atmosphere and then building them into their tissues. That's how plants grow.
Mm-hmm.
Those tissues, though, they require energy to keep going, just like we do. So we eat something, then we burn that energy. The trees, they're eating that carbon dioxide, in essence, and then their tissues have to burn energy just to keep themselves going. So it's that burning energy part. In a sense, you could think of it as becoming less efficient, just like on a really hot day, we're sweating, we're like using a lot of energy just to keep ourselves in stasis. That same thing is happening with these plants, and obviously they can't get up and move or go for a swim or something like that to cool off. They're just rooted in place, so they have to use that energy to keep themselves cool and keep those metabolic processes chugging along. All of that reduces their efficiency, and what this paper is looking at is that these trees are going to grow more slowly. It means they're going to not be able to accumulate as much carbon as we thought they would.
Mm-hmm.
So this conventional wisdom that they're just in stasis, in equilibrium, this is shifting that conventional wisdom and saying, as things get warmer, that equilibrium is going to shift. The upper limit of carbon that they can store is going to start going down.
Gotcha. Okay. And what's interesting, too, is that it's contingent on the highest temperatures that they have. So if you have a long period of sustained warmth, but it's not peaking at high levels, it won't be as bad as it
Yes.
is.
Mm-hmm.
Okay.
Several years ago, it was observed that the nighttime temperatures in the tropics were moving upward as a result of climate change faster than those daytime maximums. And people were starting to speculate, what could that mean for these plant processes and this respiration process and all that? What this paper is finding is they looked at all these different factors, and they found that daytime maximum temperature was the one that was most tightly correlated to this effect that they're looking at, this dampening down of the ability to sequester carbon.
Okay.
What that means is it's probably driven by the plants just being unable to cope with those higher temperatures. It may also have sort of knock-on effects then with mortality of these trees. If they're sitting in this place and it's exceeding their ability to live at these high temperatures and sustain themselves, those trees are going to die away, and then you begin to see a turnover in the species that are present there.
Mm-hmm.
So they talked about those effects then as these other more complicating factors. They talked about the physiology being one response. So each individual tree has some ability to respond, just like we acclimate here in Chicago, wintertime, by the end of winter, you can go out in a sweatshirt and you feel fine at 20 degrees Fahrenheit. Whereas when the first time that hits in November, you're like, oh, I need my winter coat. So they can adapt and adjust their own physiology to feel more comfortable in a manner of speaking.
Okay. And that's this issue of, just to bring up the technical terms, that this is the issue of physiological plasticity and interannual variability.
That's right.
Okay.
Yeah. So each individual tree has the ability to adjust a little bit. What you can also then see is not an individual tree, but a species has a range of individuals. And so some that are more adapted to that higher temperature may begin to persist in this place, even though individuals may die.
Right.
So that's within the species, there's a range of adaptability. And then finally, we have at the community level, as species drop out because they're not able to persist, you could have new species replace them that are more suited to those things. So that's community level shifting or adaptation.
And I guess if we're in the tropics, so there aren't many species that can move in. There aren't
Exactly,
many,
We're already at the place where the temperatures are the highest, so it's not...
And then as the trees are getting more and more tired, more and more inefficient, less and less able to digest the carbon, for lack... Is that a good word to use?
Yeah, I think that's... We can go with that.
Okay. But there's so much more carbon, so it's going to be shoved down there. Well, they don't have throats, but there's these two balancing effects.
Yes.
Okay. And what's new here is that the temperature effect is stronger than they thought. Is that right? Or was that what's new? Or is it just that they're finding the balance is a little more complicated than?
So I think we've known about this effect at the plot level for a long time, and they've been able to synthesize this data for the entire tropics and then quantify it and say, what this means is a loss of this amount of carbon in these forests worldwide. And that's a pretty significant amount. It's not a huge amount, but I think everybody was expecting the CO2 fertilization to win out. And we don't have to worry.
Okay.
These forests are going to be fine. They're sequestering more carbon. It's going to be okay as long as we don't chop them down. Now they're saying, no, we've got to really pay attention to the temperature also, not just the amount of carbon dioxide in the atmosphere. So it complicates the story a little bit.
And then there was a rainfall, or moisture was another.
Yeah, the moisture thing is cool.
The moisture thing is this. High temperatures whack the ability of trees to sequester carbon most during very dry seasons. If you have higher temperatures and a normal to wet dry season, the impact isn't as high, at least not in the trees. The impact is, however, high in the soils. Put another way, moisture impacts the carbon storing potential for trees and soil differently as temperatures rise, which is one of the reasons we really should just stabilize temperatures at this point. But here's the key sentence from the paper. Quote, in soils, moisture limitation, in other words, low moisture, suppresses the temperature response of heterotrophic respiration, whereas in trees, moisture limitation increases the mortality risks of high temperatures. So high temperatures plus low humidity really messes up the trees. But in soils, high temperatures and high humidity can mess up the carbon in the soil. This brings up an issue that I'll loop back to later in the conversation, and it's a critique I get a lot. And it's that I put too much emphasis on land management and not enough on just letting nature be. I get that, and I really want to just let nature be. But the fact is, we have already destabilized nature. We have destabilized the ecosystems that keep us and our civilization going. COVID-19 is nothing compared to the green swan of climate change. I've spent 20 years deep in the weeds of this stuff, and I've got a pretty broad understanding of the science, the economics, and the social forces at play. I don't consider myself an expert, but I've been around long enough to know who the real experts are and who's just making noise. Unfortunately, when my colleagues in mainstream media parachute into this space, they usually fixate on the wrong people, and the consequences can be tragic. It's one reason we're in this mess. I haven't had the bandwidth to produce as many episodes as I want, but I do try to make each episode worth listening to. If you think they're worth listening to as well, and if you want more and better episodes, then help me out by becoming a patron at patreon.com/Bionic Planet. I listen to some of these NPR, BBC, and New York Times podcasts, and it takes them 5 minutes to name all of the contributors, the producers, the sound designer, the fact checkers. I just have me for now, and only part-time. I am open to sponsorship if it doesn't come with strings. So for now, I'm listener supported. You're a listener, and you can support me for as little as $1 per episode and with a monthly cap. You can do that at patreon.com/Bionic Planet. That's patreon.com/Bionic Planet. You can also help by giving me a 5-star review on whichever podcatcher you access me through. Remember, the more stars I get, the more ears I get. And the more ears I get, the more minds I can reach. And we have to reach hundreds of millions of minds if we're to meet the climate challenge. We can do it if we all work together.
This kind of sets up at least 2 more steps for further research with information we already have in hand, stitching things together. So because this group has already looked at the CO2 fertilization effect, I would expect like the next big research question for them is put these 2 things together. We've got the temperature, which is making it more difficult to sequester carbon. We've got the CO2 fertilization, making it easier. What happens when we mush those 2 things together? And that would be a big kind of data crunching exercise that then they would have to verify with what they're seeing in these individual plots and look at that closely. And the thing is, these are not uniform effects, right, across the whole tropics. There will be places where one dominates and the other fades away, and then there'll be the opposite in other places. So mapping that out and figuring out like, whoa, how is this competition going to play out within these specific areas that we care about? I think that's going to be a cool study. Like I'm anticipating that's probably the next thing on their work list.
Yeah.
Even within this paper, they found these strong differences in different regions of the world.
Yeah.
And talked about the Amazon is really maybe going to get hammered.
Yeah.
Which lots of people really care about the Amazon, and there's already a lot of other things going on there that are going to affect this. So that was a scary dynamic. On the other hand, they said African forests maybe look okay. Asian forests are actually doing all right. They're sequestering a lot, and they have really high carbon stocks now. So maybe the ones that are left will be okay.
And there were differences in the type of effects, like some eating my ankles here.
I know, here comes the mosquitoes. The wind
We're having
died
the
down.
plagues here. We've got the locusts, and now we've got the mosquitoes. Okay. Continents with high carbon stocks had either large carbon gains in Asia or long carbon residence times.
That was interesting. What that suggests to me, there's not enough detail in this paper to really suss this out, but it suggests to me, based on some other work I did actually in the Rocky Mountain forests, where you would see mortality, you would see increased incidence of fires. So those kinds of effects are the things that can change this residence time. The way I interpret this is these Asian forests are sitting there, they're cranking away, and there aren't a lot of threats to them right now from those types of issues. Whereas we've seen in the Amazon in more recent years, these cases where there were these widespread fires, and those really affected the trees because there would be the presence of a drought, sort of a background condition. Then once fire gets going, it devastates a big area, kills a lot of trees, and there's no paleo record to indicate that there was any fire in the Amazon before these climate change effects started really changing
That's
the
interesting.
dynamics.
Okay, so it's not like North America where there is a paleo record.
Totally, yeah. And then also there are examples of, during El Nino conditions, some of these Asian forests, particularly in Indonesia, they are seeing big fires, and people are out there, they're burning stuff, and then the fires get out of control. That's also relatively uncommon, I think, in the paleo record. So for these tropical forests to be experiencing conditions where they can burn, that's unusual. And that would be reflected in this residence time. It means the carbon's coming in, but then it's going right back out again more quickly as a result of these dynamics.
Gotcha. Okay. Going back to the numbers here, let's see, there was, I think the exact number they came up with, was it 1 degree? Was it 16? Was it petrograms? And it was almost double. It was more than double, I think. Where was it? I feel like that interview Trump did, where he was digging around in his papers. And look, here it is. Look at the chart.
So what they looked at is they said, we measure the effect at 1 degree, and then we extrapolate it out to 2 degrees.
Exactly.
If there were 2 degrees of warming, we would anticipate this loss of a certain amount of carbon in forests already.
Here it is. Our results suggest that stabilizing global surface temperatures at 2 degrees Celsius above pre-industrial levels will cause a potential long-term biome-wide loss of 35.3
Petagrams.
petagrams, which is the same as a gigaton, isn't it? Pretty much.
Yes.
Yeah.
Mm-hmm.
And then 95% confidence interval.
And the greatest reductions are in South America.
Yeah, yeah. That's where the worst is going to come. I mean, how big is... I'm trying to remember, how big is the...
I knew you were going to ask this question, so I started looking to see how much carbon is in these forests right now.
Yeah.
And so globally, that's about 1% of carbon that's currently in forests. So it's
Okay.
shaving off that amount
Okay.
as a loss. That's just taking these temperature things into account. But I think everybody was like, this is either going to be an equilibrium or actually these forests are going to sequester more carbon. So that's a little bit of a surprising note to be like, oh, no, it's going to be less. For all tropical forests, then it's about 2.5%. So it's not huge. It's not like, gosh, this is the end of the world. But it's the opposite direction from what people expected. One of the things I've been looking at recently is this idea that we're faced with a situation where we need to have a lot more forests.
Yeah.
We need to protect what we've got, and we maybe even need to expand. And there's been a number of research papers out about this recently. There was one by a team led by Baston et al. And Thomas Crowder that came out. It really got a big splash because they were like, hey, there's like close to 1 billion hectares of land that we could just reforest and it'll be great. That paper got a lot of pushback from the scientific community saying, wait, that's way overestimated. But I think we could say the folks who work in this area think that something like half of that is actually quite reasonable and something we should be doing. That would be an expansion of forest area between 10 and 15% more forest worldwide.
So
and
if we increase the forest 10% and we lose, in terms of carbon sequestration, we lose 2.5%, it's really a 7.5%.
yeah, so that's why the implications of this paper matter for that question. We're thinking about, gosh, where are we going to find 500 million hectares of land to plant up trees or allow natural regeneration? That's to keep us within our carbon budget. This is saying, nope, you got to think about this a little bit more.
Yeah.
Because we may actually be losing carbon, or the trees that we have now, the forests we have now, they're not going to be able to sequester as much as we expected because of this temperature effect. That means we may have to expand that quite a bit more, and every hectare is going to be hard to find. It's going to be hard to convince someone, hey, you should really be planting trees here or growing trees instead of farming or having a pasture here or whatever. So that was already a tough challenge.
Right.
This makes it even tougher.
Okay.
And so those are small differences in really massive numbers, and that means it makes the job harder.
Do we know what happens above 2 degrees, or is that just, are we saying if we get to that point, it's game over? I mean,
I get asked this a lot, and 2 degrees is just this arbitrary threshold.
it's because of the Paris
We do
Agreement.
know that every increment above that, it gets worse and worse and worse. So it's not like we suddenly hit this wall and it's game over. But we do know things get progressively worse the farther we go beyond that threshold.
Yeah.
So we don't want to be flirting with that. There's something interesting about this paper. As you look deeply into it, I started to realize, okay, the pace that we get to this 1.5 degrees or 2 degrees, that really is going to have a big effect here. Because they talked about that plasticity and the community level effects and things like that. A lot of the climate scenarios that folks have been looking at, and I would say this is probably the second piece beyond that research I talked about earlier, putting these pieces together. The next stage would then be spin this through some climate models where you're actually projecting globally, where is it going to warm up and where is there going to be more precipitation and how do those things play out? So then you could really start to get a picture of what's going to happen. But if we have these things happening simultaneously, that's going to be a complex question. One issue is that because those other factors depend on the rate, for trees to be replaced over time, that takes decades or even centuries. The climate scenarios have this overshoot idea in mind. Oh, we're going to go ahead and blow past all these targets, but then we'll bring everything back down again. And trees will play a role in that. They'll be sequestering the carbon back again. But But the ability for the trees to do that really depends on how steep
Yeah.
we go up that curve and come back down. So if
Right.
it's like really sharp, like the Matterhorn, and we go up
Mm-hmm.
and it's super pointy at the top and then we fall back down again, that's
might-
really bad for these dynamics.
Yeah, they're going to be wiped out. They're gonna
Yeah,
be-
exactly. And then we'll have a lot of dead, dying forests that won't be able to shift in response to that really steep peak.
Right.
If instead it's more like a smooth curve, like Kilimanjaro, then these trees may be able to persist and all these other dynamics can play their course and play their role in this drama and may be able to mitigate that effect. So they're still around. They're still around to play that role later. We have less turnover and a more durable terrestrial biosphere that's going to be able to help us out of this predicament.
Okay. Yeah, there were two things in there too that I thought were hopeful. The temperature increases right now. The biggest temperature increases are at the higher minimums. Not
Yeah,
at
that's
the,
right. That's right. Mm-hmm.
And so that's, I guess, kind of a hopeful. We shouldn't grasp at it though. We should. You
Right,
get into
right.
Yeah, we don't want to be
Yeah.
hoping for what's it, plan for the worst and hope for the best. And I guess the other question though is they're talking about 2 degrees at the tropics, right?
Yeah.
So if we have 2 degrees, and the warming is mostly happening at the poles.
Correct.
So if we do limit global warming to 2 degrees, that would be less than 2 degrees at the tropics.
They present the results saying if we stabilize global surface temperatures at 2 degrees, they didn't mention the effect you just talked about that happens more slowly at the tropics and more quickly at the poles. So it'd be tough for me to interpret what that means
okay.
here and how that's spread across the tropics and how these things come into play.
We'll have to call them for that.
The other thing they didn't talk about, because this is just a study looking at tropical forests, but at the same time we may have a big increase in the productivity of temperate forests because the CO2 fertilization effect is happening there, but those forests have even a little bit more flexibility in the climate conditions that they can accommodate. And then we have boreal forests as well. It's more of a mixed bag there because the warmer temperatures also cause permafrost
Yeah.
thaw and emissions of methane from the ground and all these crazy things. So there's a chance of the boreal forest becoming this runaway train, big feedback loop.
You told me about the day the day we met.
Oh, yeah.
Back in Bali, I think, right? 2006 or something. You were talking about that, the boreal forest and how this, I was like, oh, Jesus Christ.
Yeah, so we don't really know how those things will play out there, but the temperate forest may have the ability to grow a lot more and soak up a good bit of that carbon. And it's also some of the places where we could reforest or expand the area of forest.
How about, is there a way, because we're in this area where we're on this managed planet, right?
Yeah.
And is there a way we can manage these tropical forests, or is that just too big of a thing to even think about? We've got these higher temperatures, you've got the water issues. Can we put
Right.
cooling sprays over there? What can be done, to help these forests through this mess
Yes.
that we're bringing them into?
I think there's a ton of things that can be done, and I do think management could play a big role in that. And land management overall. Everyone's really worried about the vast areas of deforestation that have happened in the past few decades. If those areas, though, could start to be reforested through natural regeneration or whatever, that would be the ideal approach, but plantations could also play a role. If we can get some of those areas reforested, it means they haven't lost all of those ecological functions necessarily that were suddenly stripped away. Whereas here in North America, this was deforested hundreds of years ago. There's not a lot of chance of recovering some of those ecological functions. But in the tropics, maybe we still could. There may be remnants, there may be some connectivity that could be reestablished.
Okay.
Also, in terms of this management effect, one of the big things that's hammering tropical forests is fragmentation. Fragmentation happens, a little patch gets cleared, but that ends up having a much wider effect because it dries out the forests around it. So it's been documented now actually by some of these same folks on this paper that fragmentation drives the loss of carbon from the forests around that specific patch in addition to what's lost from that patch when it's cleared. So it has this knock-on, more extended effect in the areas around it. So if we could begin to infill those fragmented areas or prevent them from happening in the first place, that would have a disproportionate benefit than just plunking a new forest out in the middle of nowhere.
Yeah, and there's just a bunch of trees. It's not really a forest, right? So looking at what we've got right now, we're in this situation. We've got the Paris Agreement, the talks are on hold because of COVID-19. Policy is frozen. Bolsonaro is burning the Amazon.
Yeah.
What policy options do we have? Like, what can we do? What are the things, when you look out at all the different possibilities out there right now, what's the most promising way that we can address this problem? Literally, they're not crickets, they're cicadas. But
what I've noticed in response to COVID is a change in mindset, and I think that's significant. I also noticed that people are still doing the work that they can do at home in terms of, let's think through what are some of the things, what are the solutions we haven't gotten to, or what's the policy work. We can sit here and think about like these policy solutions at a time when we're not running around in these various meetings and everything else. Like, it's a space for thinking things through right now, is the way I interpret it. It's also changed the expectation of what people think is possible. So before, everybody was like really quibbling about what if there's a 1% decline in GDP as a result of all these policies, and now that's all thrown out the window, right? Like, we've all been hammered in this idea of like, now that the damage has been done, maybe we could come back and do things in a different way. I think people are much more open to those kinds of ideas. They're also thinking about, how do we invest differently, things that would have been maybe inconceivable before. What if we revived the CCC program and we had people out there planting trees or recovering forests or managing forests? They could do all that work in a socially distanced way. Lots of people are out of jobs right now, so it'd be a job creator, and it could be a sort of safe industry to build up at this time until we have some sort of other resolution of the COVID crisis. And those possibilities were something that would have been hard to imagine, but now people are talking about them more actively.
Yeah,
I think that's great.
The restoration economy is here.
Yeah, totally.
Okay, I think that's it. That gives me. I can't think of anything else. Thanks for having me over here. And enjoying this beautiful day in Oak.
Sorry for
Oak
the
Park.
cicadas, but
No, they're fine. Once I got my sound levels straightened out. Okay, great. Thanks.
Jason Funk of the Land Use and Climate Knowledge Initiative, or LUCKI, closing out this episode of Bionic Planet. For more episodes, check out my back catalog and consider becoming a patron at patreon.com/Bionic Planet. That's patreon.com/Bionic Planet. There you can support me for as little as $1 per episode and with a monthly cap. The address again is patreon.com/Bionic Planet. That's one word, Bionic Planet, no dots or dashes. As always, I do have a few more episodes in various states of production, and I hope to top those off soon. And any help you can offer is greatly appreciated. Until then, I'm Steve Zwick in Chicago. Thanks for listening.